Okay, so this is Unit 5, where we're going to start talking about momentum, right? And more specifically, this whole unit is going to focus around what is called linear momentum. There is a different type of momentum for angular momentum or rotational motion. But so in this unit, we're going to focus really on linear momentum, okay? So the first kind of topic here we're going to look at is exactly just what is momentum and how does it really apply on its own. And so momentum is a term that gets used a lot in normal conversations about moving objects. So it's actually a term that gets thrown around a lot. You know, it's used in sports. It's used in just in everyday speak about how if something's moving or if there's something going, that it's just continually moving. Like for example, in sports, right? Teams gain momentum by scoring, baskets, right? Just consistently, and then they make defensive stops, and then it just keeps growing and growing and growing. Right? So that's how the real world will use the 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 word. Okay, but understand that it's not always used correctly. Okay, or there's not really a full understanding. So it is a physics term that refers to the quantity of motion that an object possesses. In other words, we like to say that it is inertia in motion. Okay, and so that's just another way to talk about how momentum or define momentum, right? So we're going to have, and if you remember, inertia is around that concept or the idea of mass. So the way to think about it is, if an object has motion, it's going to be, or if an object has momentum, it's going to be a mass in motion. And so what happens is objects with more mass, oh, and I wrote more there instead of mass. Okay, so objects with more mass and more speed, they'll have more momentum. Okay, and so here you just have two quick examples. A horse running at a speed of 10 meters per second, is it going to have more or less momentum than a house cat running at the same speed, right? And so it's going to have more. And the reasoning is because the mass of the horse is greater than the mass of the cat. Okay, note that the speed in this example was the same. In the next one, you have a horse running at a speed of 10 meters per second. Is it going to have more or less momentum than the horse of same mass running at 2 meters per second? Okay, and so is this going to have more or less? It will have more momentum because the v of the speed of horse 1 is greater than the speed of horse 2. Okay, but note that they both will have the same mass. Okay, and here they have the same speed. So what you need to understand is that momentum is dependent on two things, right? Mass, so how big the object is, and then the speed of the object. Okay, or more specifically, really it's the velocity. Okay, but we'll get into that in a second. Why is it velocity versus speed? Now, in physics, momentum is considered to be a vector quantity. So this is the reason why it's velocity, right, and not speed. So the direction of momentum is dependent on the direction of said velocity. So if the velocity of the object is a positive, then it has a positive momentum. If it is a negative, then it has a negative momentum. And that's going to be helpful when we talk about conservation momentum. All right, and so what happens is it works out that momentum is directly related to those two factors, to the mass and to the velocity of the object. And we'll address that here in 1 second once we get the equation. So the equation for momentum is P equals mv. So P is momentum. Now sometimes students will ask, how come it's not m? Well, there's two reasons. Okay, one is there's already an m for mass, right? The other is it has to do with Latin roots, and I actually just found this out, that it comes from the word impetus, which has the root patere, right? And there's your P for momentum. I found that I've been teaching physics now for nearly 20 years, and this is the first time in studying physics for nearly 20, almost 30 years. It's the first time I've really understood that, or found out that why is it P for momentum. Now, the units for momentum are just simply kilograms times meters per second, so there's nothing really special here. Okay, it's not like it's a Newton, it's not like it's, a joule. It's just literally the unit of mass times the unit of velocity. And so if we talk about some of these relationships that we like to do, okay, and so the way, if you look at the equation, P is directly proportional to mass, which means if, bigger the mass, the more momentum is. It's also directly proportional to the velocity, so the more velocity it has, okay, the more momentum it has. And then mass and velocity are inverses of each other, right? And so, again, multiple choice questions, they like to do those factors of change type questions and say, okay, if I'm changing the mass, what happens to the momentum? Or if I want to keep the same momentum, how would I have to change this mass or change the speed or velocity? Okay. And so to change the momentum of an object, the velocity of the object will have to change. Okay. Again, here in physics 1, right, this is important that we're going to assume isolated systems, which means that the mass will not change. And so what is the factor that will change? It will be the velocity. All right. And so in Unit 2, or dynamics, the dynamics unit, which was Newton's laws, we learned that a change in velocity, or an acceleration, is caused by a force. Right? That was the whole thing, F equals ma, right? And so if I'm applying a force, I'm accelerating an object. If I'm accelerating an object, right, I'm changing the velocity, right? And so I'm changing that piece. So for example, a hockey player, again, I love playing hockey, right? And so here's Tyler Seguin of the Stars, right? And so if a hockey player changes the momentum of a hockey puck, right, which is what he's doing here, so he's applying a force in that direction, which means the puck is right, this little black piece. A lot of times in hockey you use black tape, so you go black on black, so it's hard to see, for the goalie to see the puck, right? And so if I'm applying a force to the right, I'm going to change the momentum because I'm changing the the velocity of the object, right? And so a hockey player changes the momentum of a hockey puck by hitting the puck with their stick. As a result, the hockey puck not only changes direction, but it also changes its velocity. Right? Because remember, velocity has to do with direction as well as the speed. And so this puck may have been originally heading in this direction, but because he applied the force, it's now moving to the right. Alright, so here's just a quick little ranking task. Again, AP is moving towards these ranking tasks, and so rank the momentum of the following objects from greatest to least. And this is very classic. It may be, talking about which has the greatest momentum, or which has the greatest, the question just would be, what is the greatest momentum? So all we really have to do here is m times v. Right? And so we're going to assume that these are all heading in the positive direction. Okay, so if I do m times v for scenario A, it will have 4 kilograms times meters per second. If I do it for B, it'll have 6 kilograms times meters per second. If I do it for C, it'll have 6 kilograms times meters per second. So you can see here we've got a tie. Right? And then for the last cart, it'll have a 4 kilograms times meters per second. So we also have a tie there. And so how is this, will this be arranged? So our greatest will be, situations B and C, but they're going to be equal, and that'll be greater than A and D. But these are equal, right? Because this was 6 kilograms times meters per second for these two, and this was 4 kilograms times meters per second for these two. And so that just also brings into a point that sometimes on some questions they may ask you for what is the velocity that like a B has to match to match the a oral liner, right? And so the way that kind of works out is a little m could have a big V, but that would match a big V or big M's little v. Okay, and so understand that completely different size objects could have the same momentum. It's just that the speeds or velocities would have to kind of balance out. All right, so here's just another couple examples using this P equals mv formula. And so an ice skater has, or excuse me, it's one example, where we're going to do a calculation, and then we're going to kind of talk about what happens when she hits a rough patch. So you got an ice skater with a mass of 68 kilograms moving to the right along the ice at a constant velocity of 5 meters per second. What is her momentum? Well, that's just going to be very simple. P equals mv, right? And so it's going to be 68 kilograms times 5 meters per second, which will give her a momentum of, then you put in your calculator, that's not right. Let me go get, alright, so got my calculator. I had, kind of pre-wrote these notes out, but I guess I did 68 times 0.5 instead of 68 times 5. And so she would have a momentum of 340 kilograms times meters per second. Okay, again, this will be a positive momentum because it says she's heading to the right, and to the right is always positive. Now, what happens if while on ice she hits a rough patch of ice? Well, a rough patch of ice means we're going to have friction. So what's going to happen to her momentum? Her momentum will decrease. All right, and why will it decrease? Because, sorry about the handwriting. All right, so because the rough, right, surface will cause her to slow down. Okay, and I say her, but I mean it could be him, right? Ice skaters can be anybody, right? Because the friction will cause a negative acceleration, right? And that's the reasoning behind that. Okay, or her slowing down and hitting the rough patch. So this is talking about what is momentum. Next thing we're going to talk about is impulse, and then eventually we're going to keep building up towards something what is known as conservation of momentum.